Hello. I have finally finished studying drag. Wow, that took a while. Um, it was very difficult to understand, actually, but I finally understand it now, and it should be easier for you guys to understand it since I'm going to try to explain it in a bit of a more simple way. If you want to know the way that NASA, for example, explained it, since I read it from a NASA article, I will put the link to the article in the description. If you listen to this video, it will be easier to understand the article as well, since some of the convoluted terms that aren't really talked about in depth, I will be talking about. So it'll you'll be able to tell that, oh, what they're talking about here is this. Uh, I believe that this will be a good tool. If you have any notes or anything you have questions about, feel free to ask, and I will try to answer anything I can. Uh, but yeah, I think that's all. Let's just start at the basic. What is pressure? Right? Pressure is how much a liquid is pushing down an object, on an object, and actually pressure works a little bit strangely. It pushes perpendicular to whatever surface you're using. Um, no matter what. Like if you put your hand in water, for example, the pressure is going to be all around your hand. And like at the top, it'll push down. At the bottom, it'll push up. At the right side, it's going to push in left, and so on and so forth. It's always pushing perpendicular in a 90-degree angle to whatever surface it's pushing on. And that's what happens if it's a static liquid in a static, with a static object, like liquid that is moving and an object that is moving. I have to mention that when we were talking about aerodynamics and drag, liquid is also wind and air and such, or a fluid. Both of them are also like air as well, right? So, what is aerodynamics? Aerodynamics is the study of objects moving through air and the resulting motion, uh, like the resulting force on the object. Basically, that just means that when an object is moving a specific direction through a liquid, then how much is it being slowed down? How much is it being pushed up, down, left, right, so on and so forth, right? It's just how much it's being affected by the air. So that's what aerodynamics is in simple terms. And what is drag? Drag is how much the object is being slowed down from its trajectory or thrust. So if we have like a rocket here, right? So this rocket is wanting to move that way, right? So drag in this situation would be the force that's being exerted this direction, like the opposite of where it wants to go. How much is it being slowed down? Mm-hmm. That's it. That's just what drag is. And lift is actually everything else that is like when it's moving up, it's what's real lift. When it's moving down, it's lift. Left, right, it's all lift. Although most of the time when we refer to lift, it's when something is moving upwards. But it, like definition wise, it isn't actually that, which is pretty interesting. I'll mostly be focusing on drag in this video. There's also something called a coefficient of lift. I'm going to be talking about the coefficient of drag since that's what I've been studying most. I have heard that it is easier to understand though, but if you want another video on that, like I might do it sometime in the future. Maybe that's going to be the next video. Ah, whoops. I need to use that rocket later, so I would prefer not to smudge it. Uh, so there's this really interesting thing that happens with pressure and the speed of whatever the liquid is, like uh, the, the speed of the liquid moving around the object, right? When the speed is actually fast, that actually means that there's less pressure. And when it's slow, there's more pressure. So when you think of a airplane wing, uh, they actually design it on purpose to be faster at the top than at the bottom. Uh, so that means that while the air is moving, it's going to have to take the same route. The air has to go from A to B, the same, like, not the same route, same, they have to go. And since there's a shorter path, it'll be forced to move faster at the top and slower at the bottom. When you think of a faucet, for example, if you put your hand on the faucet, now there's less space for the liquid, the water, to get out, so it'll actually start ejecting faster. It's the same-ish concept. The air is forced to move at a specific speed. Uh, it's forced to get to here at the same time as the other wind. But if it's a longer path, it'll have to move faster, and if it's a shorter path, it'll have to move slower. That's just how it works. And since we do this, there's now a faster path at the top, which makes almost a suction. It makes the aircraft want to go up, which is actually completely different to how I was imagining lift would be. I was just imagining here, the wind is shooting up here, and then pushing it upwards because of that. But that's not how it works, which is very crazy. I'm going to turn down the lights. There we go. So now the you won't be able to see my face in the like board constantly. That was kind of annoying for me. Yeah. So basically, what that means is that we can manipulate the wind to try to get us to go in a specific direction, which is super useful. We do this a lot. The thing about drag is we don't want that part. We want as little drag as possible. That part doesn't help us. We want to go the way we want to go. We don't want to be slowed down by that. It's a bit of a bummer. And something that makes this even more complicated is when there's... Wait a minute, let me draw it real quick. So, there's something called an ideal fluid in physics. Wind is not that. An ideal fluid is when something has zero viscosity and zero stickiness. That basically means that it's a liquid that doesn't have any friction. You can like move like between it effortlessly. It's like if you're moving in space. There's no wind. There's nothing stopping your hand when you're moving forward, other than gravity and such. But that part isn't like the liquid, so it would be an ideal fluid, right? It doesn't stick to your hand, but air does. It sticks to the surface of the aircraft. Actually, that actually causes it to have a layer of air. So the air that's actually affecting the like the aircraft via something called friction drag, which is basically just the friction the air is having on the object. how much the air particles are stopping and bouncing off of the aircraft, it actually doesn't touch the aircraft. It's touching the air around it, which is then touching the aircraft, which is causing the drag, or the friction drag. And what makes this little sticky layer even more annoying, other than making our calculations even more complicated, since now there's this weird variable we have to account for, is it actually doesn't stick on constantly. It gets ripped off from the constant speeds and stuff, and it causes it to go in these weird whirlwinds, is what I will call them. And as you know from any whirlwind, not volcanoes without, like a vortex in water, a tornado, those pull stuff in. Same thing with these. These guys will pull the aircraft back even more because of the suction that they're causing. And you also have to account for them sticking off and new ones having to stick on, which also again make it a lot more complicated. So yeah, these guys are annoying. That's just how it is. Uh, yeah, there's also some other part of drag. It's called form drag. Form drag is just, it's more easy to explain and understand if we think of water. When you're moving your hand through water, the amount of viscosity the air has is slowing down your hand so much that it feels like it's pushing in on it. That's not because of the friction. That is because it's just such a viscous thing. It's the same with honey. If you had to move your hand through honey, that would be incredibly difficult. There's still that effect with air, like the amount of viscosity that has. That's basically what um, form drag is. The form of the aircraft is what affects that. If you think of a spear that goes through infinitely easier than a plate or a frisbee that is on the opposite side, right? So that's basically what form drag is. It's uh, quite complicated to calculate since there's a lot of variables. Same with friction drag. You'll learn very quickly that there are no easy ways with any of these. They're all going to be complicated and they're all going to be a pain in the ass to calculate, especially if you have to calculate them individually, which you will have to do if you don't have a high tech computer or already know the amount of force you're applying, and then you can just reverse the equation to get the coefficients of drag. I'll go into depth with that a bit later. Um, the amount of viscosity is actually it's expressed with something called the Reynolds number. You don't need to know it. It's basically just how viscous something is. This number also changes depending on the speed of whatever object we're thinking of, and also like the shape. The shape and the liquid that it's going through. We also have wave and ram drag. Um, Wave and ram drag is what happens when you're approaching the speed of sound, the sound barrier. It's basically where there is what are they called? Shockwaves, I think. Yeah, shockwaves moving through the object that slow down the aircraft. Yeah, that's basically what wave drag is. It's the magnitude of these. How did I already forget that word? Huh? It's the magnitude of the shockwaves and the vibrations. Um, and then there's also the ram drag, which is basically the air that's being sucked in by the thrusters. So thrusters for spaceships usually have their own oxidizers inside of it, which means that this doesn't matter. But I'm pretty sure that when it's being ejected into space, when it's still in air, they just use normal fuel. So they're not oxidizers, so they have to get air from the outside, which means that as your like the thrust is like pushing you down, the air being sucked in to fuel the fire is also influencing the drag. Although usually when we're doing the equation, uh, we just put that into the net thrust value. We just subtract it. Um, yeah. Also, when you're trying to get the ram drag, no, was it ram? No, the wave drag. Yeah, the wave drag. You calculate that using the Mach number of flow. Um, I don't really know all that much about that, uh, but that's how you do it, apparently. You'll have to go into more in depth with that, or I can again talk about it another time. Um, but it would be too long of a video if I also had to go in on that, so I'll have to skip past that for now. We're actually getting into how to calculate the drag now. So, the drag equation, what is CD, the coefficient of drag? The coefficient of drag is where you clump together all of the difficult variables, like the friction drag, the form drag, the wave and ram drag, and so on and so forth. You collect all of those variables and then you put them into one variable, which is what you are going to use um, as kind of a simplified version of this calculation. If you want to get the CD, you have to collect all of these values, and they actually also change depending on some of the other variables that you have to choose in this, which I'll like talk about more later. So here it says D equals CD times P times V squared times A divided by 2. Yeah, it's quite a short equation, but let me go into depth with what all of the different things are. So P is rho, which is the density. I'll tell you later why we call it rho. What the hell? Why not just now? Rho is called rho because D is usually already like known as distance when you're calculating drag and aerodynamics. So having two of the letter D would complicate things and make things a lot more convoluted. So they just go with I think it's a Greek letter, which they're going to use instead. And then we have v squared, which is the velocity squared, times the area, the approximated area. Uh, Approximated area, it's called that because there are actually multiple different choices you can use to put in that equation. No matter which one you of the areas you choose, the drag will stay the same. I'll explain why and how later, and then you divide that by 2. And then multiply it with the CD, which is all the variables. So, what is reference area? So, when you're trying to choose which area fits best for the equation, it depends on which one is affecting the object the most. If it's mostly skin drag, it makes most logical sense to use the total surface area. But if it's form drag that's the primary like drag, then using the frontal area makes more sense since form drag is very heavily dependent on the front side of the area, like the object. But no matter which one you choose, CD, like the clumped together variables, will just take in the rest of those numerical values. So let's say we chose the total surface area with since skin drag and like friction drag, they're the same thing, was the most contributing factor. Then CD takes the remaining stuff that would have gone in for frontal area for the form drag, and then it gets put in there instead. So it kind of equalizes it. It never actually changes the result, no matter which one you choose, but it's just which one you think is easier and fits best. You have to like say which one you're deciding to use if you're putting it in a paper, um, just so people can like reuse it. If you're if someone thinks that you're using the frontal area form drag and they use that when you actually use skin drag, that would mess up the equation and you would get a wrong number at the end. Um, but as long as you understand which one you're using and you're accounting for that with the CD, then it should be fine. Uh, yeah. There's also rho times velocity squared divided by 2. That's called the dynamic pressure, which is a part of Bernoulli's pressure equation, which is something that's I found interesting. It's a part of also drag, but it isn't that important to know. That is it. That is drag simplified 101 part 1. Yay. Um, I hope it was easy to understand, although it probably wasn't. If you have any questions, I'm happy to answer all of them. And without further ado, see you next time.